Recording in progress.
Okay, now it's good.
Okay. So, good afternoon, everyone. Welcome to the distinguished seminar series on data science and artificial intelligence, hosted by the Department of Computing and the Research Center on Data Science and AI at the Hong Kong Polytechnic University. Today, we are very pleased and honored to have Professor Baochun Li to give our seminar on this series. Professor Baochun Li received his Bachelor of Engineering degree from the Department of Computer Science and Technology, Tsinghua University, China, in 1995, and his Master and PhD degree from the Department of Computer Science, University of Illinois at Urbana-Champaign, USA, in 1997 and 2000. Since 2000, he has been with the Department of Electrical and Computer Engineering at the University of Toronto, where he is currently a full professor. He holds the Bell Canada Endowed Chair in Computer Engineering since August 2005. His research interests include cloud computing, distributed systems, data center networking, and wireless systems. Professor Li has co-authored more than 410 research papers, with a total of over 21,000 citations and an H index of 83 and an I-10 index of 280, according to Google Scholar citations. He was the recipient of the IEEE Communication Society Leonard G. Abraham Award in the field of communication system in 2000. In 2009, he was a recipient of the Multimedia Communication Best Paper Award from IEEE Communication Society, and a recipient of the University of Toronto Maclean Award. He is a member of ACM and a fellow of IEEE. Today, he's going to bring us a seminar titled 4 Guiding Principles Towards Designing Good Real-World Systems. So without further ado, let's welcome Professor Li.
Thank you very much. Thank you for the introduction. And it is my distinguished honor to be here today and share some of my thoughts about designing good real-world systems. So the title of today's talk is 4 Guiding Principles Towards Designing Good Real-World Systems. And that seems more like a clickbait. So typically when you go to a YouTube video, sometimes you see the 7 bad things about this car. You know, that's typically a bit clickbait. But there are some of the resources that may not be a clickbait. One of them is a book, and that is authored by Professor Jordan Peterson. And the name of the book, the title of the book is called 12 Rules for Life, an Antidote to Chaos. And here, we can do something similar. We can do 12 rules for system design, for example. But we don't really have that much time today. So probably we have about 45 minutes today. So we can only share up to 4 guiding principles for real-world system design. And rather than an antidote to chaos, we have an antidote to bad performance. So designing a real system, a real-world system, is pretty hard because it actually is not only involving engineering, but also involves a creative process. And just like anything else that is creative, there are some ideas, in my personal opinion, that can actually help us to actually lead to good designs. And where do we start from? Well, you might think of something like simplicity. After all, Albert Einstein once said, out of clutter, find simplicity. But, well, probably not. It can be an overarching philosophy, but is probably a little bit too high level. So we probably don't want to just say simplicity. Let's try to design something simple. So what are these four guiding principles for real-world design? Now, based on my personal opinion, I believe that we should present these guiding principles in no particular order. In other words, nothing is more important than some of the others. And the reason for that is because the very first guiding principle, idea number one, is to randomize. I would like to start from something called network coding. So network coding has been around for about 20 years, 2 decades, since about 2000, when Professor Raymond Young proposed it in his seminal paper. And it is a pretty good idea, assuming that each one of these links in the network graph, in particular, directed network graph, where each link had a source as a destination. And if we don't have any errors on these links, and if we want to do multicast in an arbitrary graph from one source to multiple destinations, in this particular case, we have 2 destinations and 1 source. And what the question is, what is the maximum achievable throughput if we want to do multicast? If we don't do anything related to network coding for this particular graph, which is the famous butterfly example, you have X1 and X2 going into a shared bottleneck. And that shared bottleneck, you can either send X1 or you send X2, and you cannot send both of them at exactly the same time. So with network coding, what we can do is that we can try to code them up. We can actually try to have a coding operation in an intermediate network switch. In this case, when we have X1 and X2 sending into that particular switch, that switch can actually do something like X1 plus X2, where plus can be as easy as exclusive or we can actually have a plus operation defined in the Galois field. And in this particular case, with network coding, we can actually achieve a throughput of 2 rather than 1.5, where we have to send X1 and X2 alternatively. But the question is, how do we compute the coefficients to achieve optimality? So previous example, we had X1 plus X2, but in the general case, we might want to add these coefficients just to make sure that the final result can be decoded. It can be a matrix with full rank. So how do we actually try to do that? We could design deterministic coefficient assignment algorithms, but these assignment algorithms have to have full knowledge of the network graph, which is okay in theory, but it is not a very good assumption in real-world systems. So if we actually try to apply network coding in real-world systems, we will have to randomize. We will have to do something called random network coding, and we have to generate these coefficients randomly. And that's something that is solving the problem of assigning coefficients and still have a high probability, we don't have a guarantee, but we have a high probability that we're able to decode. And it's a very simple idea. It was published in 2002 timeframe, and it brought network coding a giant step towards real-world implementations. Another example that is very different from network coding, that is in a completely different category, is when we're trying to design web servers. If we have a lot of load, we have a lot of requests coming into our web server, of course, we need to have multiple of these servers serving these requests. But the question is, how do we actually try to direct individual requests to different servers in a load-balanced way? We could have, again, heuristics, but in this particular case, the simplest idea is to randomize. All we need to do is to reuse, for example, the IP address of the request we generate a hash value of that IP address, and we connect, just try to send to the server corresponding to that hash value. Another completely different category, an example in a completely different category would be lottery CPU scheduling. This is a very simple scheduling discipline inside operating system design when we actually try to share the same CPU among multiple processes. If we have different weights, for example, process A is 3 times as important as process B, if this is the case, how do we actually make sure that process A and process B and all of the processes have its fair share? Now, one possibility to do this is, again, to randomize. All we need to do is we issue lottery tickets to these processes. And process A, because it's more important, probably gets 75% of the lottery tickets, and process B will get 25%. And then every time we have a scheduling opportunity, all we need to do is to try to run the lottery. And whichever process that wins the lottery will get the CPU for the next slot, for the next time slot. And that is a very simple scheduling discipline because it's stateless. It doesn't require any states maintained for this particular scheduling discipline. And there are many other real-world examples. For example, if we have a wireless broadcast medium and we want to resolve contention, of course, multiple nodes cannot send at the same time. And if a node, when it tries to transmit, it detects that there are other nodes transmitting at the same time, how does it back off? So we of course, can set the back off time randomly. In the area of, again, operating system design, when we actually try to make it a little bit more secure, when we design virtual address spaces, we can do something called address space layout randomization, just to randomize the assignment between virtual addresses and physical addresses so that we have fewer opportunities for malicious attacks, for example, buffer overflows. And in general, randomized algorithms may avoid maintaining states and improve the performance because they are simply very, very simple. And that echoes our original high-level idea of simplicity. If we actually have something simple, maybe it's actually pretty good. Not only it's actually good, it has been shown, for example, in theoretical computer science, when we analyze algorithms such as quicksort, if we design the algorithm so that we select pivot elements uniformly at random, we are able to achieve the order of n log n of time complexity related to QuickTime. And that is a very powerful way of designing algorithms. And in fact, there's a category of algorithms called randomized algorithms, and they solve a lot of problems that cannot be solved deterministically with deterministic algorithms. Another very good idea in the design of algorithms is the Monte Carlo method. It uses randomness for deterministic problems that are difficult to solve. And it's a general method with general category of algorithms. And one particular example of that category of algorithms is the Monte Carlo tree search. Monte Carlo tree search is one specific algorithm that uses the general principle of Monte Carlo methods, and it was proposed in 2006. And before 2006, before it's proposed, the ability for computers to play Go is way lower than human beings, way worse. And once Monte Carlo tree search was introduced, the ability for computer to play Go is dramatically better. And of course, we all know the recent events of AlphaGo, and all of that, even though they're rather sophisticated, they're based on Monte Carlo tree search. So randomization and avoiding maintaining states is idea number one. It's a good idea number one. It not only is simple, but in a lot of cases, it actually can solve problems that you cannot solve with exactly the same time complexity using deterministic algorithms, or it actually can perform way better than deterministic algorithms. So try to randomize and try to avoid maintaining states as much as possible. But what if I have to remember and maintain some states? Well, one tip right here is to use, again, a simple idea. And that simple idea, even though we have to maintain states, is something called soft states, which is an idea that actually tries to say, I'm going to maintain these states, but I don't need to tear down the states. I don't have to forget these states. They will be forgotten after some timer expires. So that's something that is very important, that we can try to design, even with states, even if we need to maintain states, we can try to design something that is very simple. And of course, if you need to keep the states going forward, all you need to do is you need to refresh from time to time. So that is idea number one. Now, what about idea number two? Well, here I'm concerned with the use of layers. I like the idea of using layers, but I would say, it's just my personal opinion, of course, that we should actually have no more than 3 layers. Why do we actually count the number of layers? Well, there's the famous or the infamous ISO/OSI model that is shown in all of the traditional textbooks on computer networking, all the way starting from application layer to the presentation layer, session layer, transport layer, network layer, data link layer, and the physical layer. All of that would be in the textbook. Rumors said that it's actually designed by a committee, and there are saying that things designed by a committee may not be so elegant or so useful in the real world. So what we really have in the real world, and what we really need, probably would be just 3 layers. We have a general link layer, where you typically put implementations of this particular layer into the hardware or firmware in the baseband, for example, of modems and cellular modems. And you have a network layer, and that would be in the internet protocol, IP. So that takes responsibility for scheduling and for routing. And then you have everything else on top of the network layer. For example, the transport layer, such as TCP, we run it as an end-to-end protocol. So we can call all of these protocols that are only on N hosts, we can call them the end-to-end layer. And where's the physical layer? Well, the physical layer could be part of the link layer because it's implemented inside the hardware. And this is not my idea. This is actually borrowed from Chapter 7 of Principles of Computer System Design and Introduction. And I think it's a great idea because it doesn't try to overuse the idea of layering. But the question is why? Why don't we have more than 3 layers, in my personal opinion? The question can be answered by this famous end-to-end argument. And this is, of course, started from the 1984 paper, the seminal paper, titled End-to-End Arguments in System Design. And the end-to-end arguments, if you're not familiar with it, is basically saying that if we have a feature or a function, and we wanted to implement that function, the question is, where do we implement that feature? And the end-to-end argument said, please try to implement it in the application layer, or in an end-to-end layer, and which is above the network layer. Try to do it at the end-to-end layer. The only exception is if you can implement it in the lower layer, can get a performance enhancement. If you cannot get a performance enhancement, do it in the end-to-end layer. Otherwise, if you're sure that you can get a performance enhancement, then probably a part of the feature, the incomplete version of that feature, we can put it in the lower layers. An example of that would be something called careful file transfer, and that's part of the paper, 1984 paper, where we just need to transfer a file without any errors. The question is, should I do it from end to end? Should we implement this reliability guarantee on the 2 hosts, or should we do it in the lower layers? And in this particular case, we know the answer is to do it in the lower layers. And the reason for that is because it actually helps improve performance. If we know that the packet is incorrectly received, all we need to do is to retransmit that packet rather than retransmitting the entire file. And the end-to-end argument can be made in a lot of other places as well. It can be made elsewhere. For example, error control. That's what we had in our previous case when we have the careful file transfer. And the argument here is it is best done in the applications unless there's a performance improvement in the lower layers. Encryption, again, best done in the applications unless you can show a very good performance gain if you do it in the lower layers. Diffie and Hellman, Needham Schroeder protocols, they're all doing it from the end-to-end layer. In the database community, two-phase commit protocols, again, this protocol is designed without any assumption of reliability, FIFO sequencing, duplicate suppression in the lower layers. So this is designed to be something that is robust enough so that you don't really have to support it by offering features in the lower layers. And that, again, follows the end-to-end argument. Believe it or not, even in hardware design, RISC architectures, we're actually doing something that is very similar to following the end-to-end argument in the sense that we don't really need to anticipate the application requirements for introducing esoteric features or instructions. We don't have to have a multimedia instruction just to accommodate a small percentage of multimedia applications and make them a little bit faster. And that is the argument originally when the designers of RISC architectures proposed. And so far, right now, all of our edge devices, cell phones, and so on, they're using ARM, which is using a RISC architecture. Now, what about 4 layers? Can we actually make it 4 layers? Can we actually introduce a layer between applications and operating systems? Well, can we actually call it a middleware, for example? Well, it turns out that the term middleware was getting more popular as we move from the late 1990s into the late 2000s, but the popularity faded starting from around 2010 and 2011. So right now, nobody's talking about middleware. And why? Well, because right now what we have is we have some of the frameworks to implement the traditional features that typical middleware layer is implemented. And the difference between frameworks and middleware is that with middleware, the original designers, they thought you're going to have to design applications based on middleware. But with frameworks, you don't have to. You can choose to use this framework A or that framework B, or you can choose to directly develop over the operating system API. You don't have to use any frameworks if you prefer to do so. So frameworks are optional, where the middleware is a traditional layer, and it's not optional. So again, it is way better to have something optional rather than to have more layers. So the idea number 2 is to cut down the number of layers in your design. You don't really need that many layers. 3 layers would be good enough. There's a corollary to this particular idea in the sense that we should use software unless performance is not good enough. And there's a case in point example, and that is machine learning. So in machine learning, we kind of follow that principle, saying we should actually put features into software unless the performance is not good enough, and only in those cases we should move into hardware. So here's an example. On the left-hand side, you have a traditional way of implementing machine learning training workloads. These are implemented using TensorFlow on top of TensorFlow or PyTorch as frameworks. And the framework would be something that we use to train the machine learning workload. And it turns out it's too slow if we're using just CPUs below the operating system kernel. And now what we can do is that we can actually try to move some of the features that we typically implement in CPUs into GPUs. And if it's still too slow, then we can try to move additional features into multiple TPUs. And rather than having TensorFlow on top of GPUs, now we have TensorFlow supporting cloud or edge TPUs. And we can have a just-in-time compiler to actually try to compile into the instructions for the TPUs to execute. So that's something that is responding to the lack of performance. And if we can actually do it in software, we don't have to move these features into hardware. And only when we find out something is too slow, and then we move into hardware. And of course, those other parts, TensorFlow, there are many, many features in TensorFlow that do not really need a performance improvement, then we don't have to move them into hardware. So implementing more functions in hardware, but only when they definitely help you improve the performance of the applications that we run. Now, that is idea number 2. Have 3 layers, but not too many. Idea number 3 is very similar. We want to use hierarchies. I'm a big fan of using hierarchies to design something in the real-world system, mostly because hierarchies get us something that is more scalable. But the question is, we should not have more than 3 hierarchies. What are the examples in the real-world systems that have actually 3 hierarchies? Well, Network Time Protocol, NTP, comes to my mind. It actually had 3 layers in its hierarchies. I would probably avoid using the term layer, even though it is a particular layer in the tree or in the graph of hierarchies, because it's very different from the layers that we talked about in idea number 2. So in this particular case, if we have 3 different hierarchies, the top, the root, will be something called stratum number 1, and that would be synced directly with atomic clocks. And the second hierarchy is synchronizing with the top layer, and with the top hierarchy. And the bottom hierarchy would be synchronizing with the second hierarchy. So that would be the design of Network Time Protocol. And of course, this is not the only example that actually uses the 3 hierarchies. We actually have lots of other examples, such as the domain name systems. Again, we have 3 hierarchies: root servers, organization servers, and finally, authoritative name servers. If you think about something related to security, such as certificate authorities, CAs, we again have 3 hierarchies. We have root certificates, intermediate certificates, and certificates. And finally, related to web services, we again have 3 hierarchies. We have regional servers, we have edge servers in content distribution networks, and finally, we have the clients. And all of these systems are wildly successful. They use 3 hierarchies in their designs to be scalable in real-world designs. So we don't have performance bottlenecks in these very, very scalable designs. But the question is, why do we limit ourselves to only 3 different hierarchies? Why do we actually try to do this? Why not use something that is a little bit more in terms of the levels in the hierarchical design? Well, in my personal opinion, 3 is a good number. It is scalable enough based on our real-world experiences. I've just shown you 4 different systems that are wildly successful, and the complexity for more levels is simply not necessary. So hierarchical designs are conceptually easy, but very difficult to implement correctly. And if we want to implement a hierarchical design, even with just 3 different hierarchies, there are many things that we must do. It is actually very sophisticated. It's very complex to implement these. At a very high level, if we actually just use a few examples, one example is caching. We have to cache aggressively in the lower hierarchies, in the leaf nodes, for example, to avoid congesting the root. Otherwise, all of the requests will go to the root, and the root will be overwhelmed. So we need caching. And the nodes in each hierarchy should depend only on their parents for proper execution. There should not be too many different kinds of dependencies. And in a hierarchical design, it is tempting to use leaf-to-leaf communication. However, in my personal opinion, leaf-to-leaf communication, it is very expensive to support. However, you might say, oh, why? We have something called peer-to-peer. Isn't that something that is leaf-to-leaf communication? We're just communicating across different devices. Rather than using the more traditional client-server model where we have to always relay from the server. So which one is better, peer-to-peer or client-server? Well, this argument may not be a very good, interesting argument because client-server models have already won. Right now, not too many systems are using peer-to-peer. We're mostly just trying to use web services, and that's a client-server model. But if we actually change the argument a little bit, for example, we can actually call it permissionless blockchain. That is peer-to-peer. Or we can actually call it cloud computing. Well, that is client-server. Now, which one do you think is the best deal? Which one is a good design, a real-world design? Well, if you actually look at it, peer-to-peer or permissionless blockchain is typically a slower design in terms of its performance. And if we actually try to use cloud computing or client-server model, typically it is a faster design. But not necessarily always that we actually choose to use a client-server model. For example, if we change the scenarios to something like traditional routers versus software-defined networking, well, traditional routers, they are running their protocols in a peer-to-peer manner when they exchange information across neighbors of the routers. And software-defined networking is trying to say, let's separate the data plane from the control plane, and let's run the control plane more like a server. So let's try to use more of a client-server architecture to run software-defined networking protocols. But so far, it doesn't seem like traditional routers are breaking at all. It doesn't seem like the migration to software-defined networking is very, very quickly. It's very fast. So why is that? Well, the traditional routers, they're more fault tolerant. When you actually have problems, it is actually more resilient to these problems. While if you use a cloud computing or software-defined networking kind of a client-server model, we certainly have a central point of failure. So if we're taking it from a security perspective, if the servers are attacked or under attack, it will be down, and when it's down, for example, iCloud when it's down, or Apple Music when it's down, then nobody can actually try to connect into it, and the service will be down. So it is a more of a less resilient to faults and failures. So that is idea number 3. The idea number 3 is we use 3 hierarchies and try to limit our use of peer-to-peer or leaf-to-leaf communication in these 3 hierarchies in the special cases where we do require fault tolerance. So a corollary to idea number 3 is to use the cloud as much as possible and only use peer-to-peer when it is absolutely necessary. So that is idea number 3. Now, the final idea that I would like to share today is idea number 4, and that is the use of pipelines. Traditionally, we wanted to use parallelism with more processing power, more CPUs, or probably using a GPU, and each GPU with thousands of execution units, and that will encourage parallelism, and that will make it faster to run some of the tasks. But there is a critical and important assumption right here that we have to make. The assumption is that this particular task that we try to parallelize will have to be broken up into multiple independent subtasks. And that is an assumption that we have to use to encourage parallelism, to actually have parallelism. And one example of parallelism is downloading images into a web browser, which HTTP2 or in the future HTTP3, we are downloading these images completely in parallel because these tasks of downloading images, they are very, very independent. Downloading one image does not require any information from the downloading process of a different image. But the question is, what if this assumption does not hold? What if the subtasks are dependent on each other in the sense that one subtask cannot start until another subtask ends. And that is sort of like a chain of subtasks. You are having the later subtasks depending on the earlier ones. And that is something that you cannot simply divide these subtasks into different processing units, such as CPUs and execution units in GPUs. You're going to have to do something else. And there is a very, very old and traditional idea, and that is pipelining. And pipelining is a very traditional idea. In fact, it is something that is as traditional as just traditional parallelism without using pipelining, but it is easily forgotten. So what is pipelining? Well, pipelining can help us to increase the throughput if we have sort of like a special feature when we have the subtasks in our tasks. Our assumption with that special feature is a subtask depends only on the previous subtask in that particular chain rather than having too many other dependencies. So if this is the case, then you simply have a chain of subtasks, and over there we can actually use pipelining parallelism to increase the throughput. In this particular example, we have on the top, we have the blue circles, processor 1, processor 2, processor 3, and processor 4. They can run subtasks independently. And then over the vertical axis, we have the time steps. So we're migrating to the future going downwards. So in this particular case, when we are doing, what we're doing here is that for task number 1, since we have 4 different subtasks, what we can do is that we can put the first subtask and run it on processor 1, and put the second subtask and run it on processor 2. And while the second subtask of task 1 is running on processor 2, the first subtask of task 2 is at this time running on processor 1. So this is called filling the pipeline. So if we are able to fill the pipeline, as we have shown in this figure, then we're running 4 different tasks concurrently, even though we're running different subtasks belonging to these 4 different tasks. And this is used in many real-world examples. For example, if we're trying to improve the performance of our CPU design, a very conventional way of improving the performance is instruction pipelining. If we have something like a 4-stage pipeline, and if we have 4 subtasks of executing a particular instruction, what we can do is that we can separate these 4 subtasks and execute them on 4 different processors. And for example, the fetch would be the first subtask, decode, and then execute, and then finally write back. These are the 4 different subtasks. And we use exactly the same idea as before, except that the timestamp right now becomes the clock cycle. And that would be a very good way of filling the pipeline and improving the performance by using multiple of these execution units inside a particular CPU. And this is, of course, not only limited to a CPU design. We can actually try to use it, for example, in a cloud or edge TPU, a tensor processor unit. And this is because that a typical operation that is typically executing in the TPU can also satisfy the assumption that individual subtasks, they are only dependent on the previous subtask, making it a chain of subtasks. Why? Because we're typically trying to process some input data, some matrices that we have. And when we process it, we typically go through multiple layers in a deep neural network. And for each layer, we do a multiplication, we do some addition, and then we do some multiplication to the next layer, and so on. And now we can divide this entire sequence into multiple subtasks. And that means that we can actually try to use pipelining parallelism to improve the performance of executing these operations belonging to different subtasks. So if we divide data into multiple slices or multiple mini batches, what we can do is that we can actually, for each one of these mini batch, we can call it a task, and we feed that particular batch of data into this task, and we can actually try to use exactly the same idea as before, while the y-axis is the clock cycle going forward, and we can fill the pipeline just like before. And this is actually one of the major reasons why a tensor processor unit is actually faster than a GPU, because it actually took advantage of pipelining parallelism to actually process tasks in different mini batches at exactly the same time when the pipeline is filled. And not only that, if we actually expand the horizon of our discussion beyond the TPU into something in the area of distributed machine learning, we can also, believe it or not, use pipelining parallelism. And this is actually a paper that is actually just recently published in ACM SOSP 2019. But even though this is just a recently published paper, with the speed of progress in the area of distributed machine learning or system support for distributed machine learning, this has already been integrated into major frameworks, such as PyTorch, starting from version 1.8. It already supports pipelining parallelism. So what is the idea right here? Well, the idea right here is that now we have multiple workers, and each worker is able to do its work. And what we need to do is we need to have a careful design of dividing our subtasks so that we can eventually satisfy the assumption that the next subtask is only dependent on the previous subtask in the chain of subtasks, and then we can actually try to fill the pipeline. It turns out the task of training a deep neural network involves the forward pass and then back propagation, the backward pass. So for each one of these tasks, for example, task number 1, we try to have a forward pass and a backward pass. But for each one of these passes, what we can do is that we can divide individual layers into the different workers. If we have, for example, 5 layers, we can divide it so that the first layer belongs to worker number 1, second one to worker number 2, and so on. And now each one of these subtasks will be executed by individual workers. And of course, we still have this back propagation, and all we need to do is that we need to have a longer period of time to fuel the pipeline. But as long as we're able to fuel the pipeline eventually, so that we can try to maximize the throughput of using pipelining parallelism, then we dramatically improve the performance of using multiple workers to train a workload in the context of distributed machine learning. And this is a very interesting but a very simple idea of just applying pipelining parallelism, because we do have the assumption satisfied that each subtask is dependent on the previous one. So today, I have talked about 4 different ideas, 4 guiding principles for real-world system design. And these are just my personal opinions, and they're not really, kind of cast in stone. You can feel free to disagree with me. Just to summarize, the first one is to randomize. And because of that principle, I'm also randomizing my 4 different guiding principles. Neither one of these are more important than the other. We're just randomizing the sequence. And randomization helps us to avoid maintaining states, making it much simpler to design a real-world system. But also it helps us to improve performance when deterministic algorithms cannot outperform randomized algorithms. The second idea is to use layers, but no more than 3 layers. So don't feel obliged to introduce additional layers into your design. Rather, you try to use something like frameworks, which is an idea that says you can use it, but you don't have to use it. You don't have to use this particular feature. And that means that it's just a framework or a component or module that is available to you in exactly the same layer, rather than the layer that you have to use. The third guiding principle for real-world system design is to use hierarchies to be more scalable, but no more than 3. And the corollary to that particular guiding principle is we have a debate between using sort of a peer-to-peer design or a permissionless blockchain design or a traditional router design or a client-server design when we have cloud computing or software-defined networking. Again, try to use a client-server model unless you wanted the benefit of a peer-to-peer design. And in our discussion, we have shown one example of that benefit, which is fault tolerance. And the fourth idea is to use pipelines. And we have shown you an example of traditional CPU design and a more state-of-the-art TPU design where pipelining parallelism is used. And finally, in distributed machine learning, right now it's the state-of-the-art. It's already part of PyTorch, for example. We're also using pipelining parallelism. So pipelining is something that is a very old idea, but people can easily forget about these ideas when they design kind of faster systems. So fundamentally, I believe that system design is all about trade-offs. There are no absolute correct designs or absolute bad designs. And these trade-offs are between more abundant resources and scarce resources at the bottleneck. So these trade-offs can involve, for example, the trade-off between time and space and cost. For example, multiplexing and virtualization, we're basically saying that we're using more time, probably more space, but it costs much less. Parallelism, again, we're using more computation power, but it takes less time to complete. It improves performance, but we have to sacrifice the computation power. And batching, again, a design principle where we have trade-offs, but here we're trading off the response time for the system throughput. But in real-world designs, we care about things that are beyond performance in most cases. For example, we care about scalability, modularity, extensibility, and elegance of our design. We also care about something like future-proofness. We want to have the ability to accommodate rapid technological change, and we also want to have the ability to try to accommodate varying market conditions, because these market conditions may also dictate some of the changes to the design, and we want to accommodate that as much as we can. In other words, our design should be more flexible, should be more accommodating for future design changes. And some of the design changes can also be coming from international standards, which themselves, they change very slowly. They also impose constraints. Sometimes your design will have to conform to these international standards so that you can be interoperable with the other systems that other people designed. So these are some of the concluding remarks that I have for you. And today, I would like to thank you for attending my talk, and I will be happy to accommodate any questions. Thank you.
Yeah. Thank you, Professor Lee, for a very insightful and a very entertaining talk, like the last one. Okay, so now we're open for questions. You can either unmute yourself, raise your hand, or you can type your questions in the chatting box. Okay, so there's one raising hand from Wang Senghua. Yeah, so you can unmute yourself and raise your questions. Speak out.
Hello, Professor. Thanks for giving this wonderful talk. Here I have a question. In your idea number 1, you mentioned Monte Carlo algorithm. I know that this kind of algorithm is a randomized algorithm, whose output may be incorrect with a certain probability. If we apply this kind of algorithm in our system, will the error affect the system?
Well, typically, if you have something like Monte Carlo tree search, for example, you actually try to run many different iterations. So if you are not exploring the correct path, when you go all the way to the leaf node for your exploration path, it is okay, because the next time you might be able to get a better result. So when we're randomizing, that's exactly the guiding principle. When we're randomizing, we're actually trying to make it easier to explore more paths that we have. And rather than using a heuristic to try to direct how we explore multiple possibilities. Now we're actually trying to explore them in a randomized way. So even if it's not optimal, in your case, not correct, it's going to be fine. It is not a big deal because we are going to have a lot of different iterations in our algorithm.
Okay, thank you, Professor.
No problem.
Okay. So again, you can either raise your hand if you have questions to ask Professor Lee, or you prefer to type in your questions. While we are waiting for questions, maybe I throw in a question myself just to keep Professor Lee busy. So you talked about the performance. Well, the four principles, they're very helpful for designing efficient and efficient systems in terms of performance. What about, another thing people that talk about a lot today is about explainability, especially for machine learning systems or hierarchies. So can your principle help the explainability, or what's your view on that?
Well, explainability would be something that is good to have, but it's not. Well, first of all, my four ideas are certainly not going to help too much on how the models are explainable or more explainable than before. And it is certainly a very interesting research topic that we have. But it's something that is good to have, but it's not, in my personal opinion, not something that is a must-have. If we care more about, for example, the results rather than how explainable the model might be, this is going to be sort of like a desirable feature, but not a must-have feature. While if we actually try to apply something in the real world, it is certainly great, for example, in autonomous driving, to have something more explainable, so that if we make errors and we make mistakes, we're able to find out what is the root cause for those mistakes. But sometimes it is good enough to put in something that is working in the production systems. And over there, it is more related to how we actually try to make sure that the real-world system works, rather than having the desirable feature that when we have a breakdown or having a failure, what is the root cause? So it's desirable, but not a must-have.
Okay, thank you. There's a question from Liu Sen Biao. The question is, does randomness may lead to uncertainty in the answer?
No, so the randomness does not lead to uncertainty in the answers. The randomness is introduced in the actual design of the algorithm. For example, when we're trying to randomize the back-off timer, when we're backing off and resolving contention, eventually the node will still be able to communicate. So it will not be starved. So there's no uncertainty on whether or not it will be able to communicate. It will still be able to communicate, but we are trying to use a very simple way to back off when we design it as a randomly generated back-off timer. And the same applies to something like quicksort, in my example, where you have random selection of pivot numbers, and that dramatically improved its time complexity, but the final result of quicksort is still correct. We still have the result of the array of numbers sorted. So randomness is something that we introduce, but it does not affect the correctness. Now, it also, if you actually try to define correctness as something that is a sort of like a guarantee of a perfect property. For example, if we actually try to use CPU lottery scheduling, if you say correctness meaning that we have perfect share, a fair share when we try to allocate processes to different CPUs. In that case, no, we are not able to offer a perfect fair share to each one of these processes, for sure, because we're just throwing a dice, we're running a lottery. So we can't guarantee that perfect fair share. So that is a desirable property, but we are not able to guarantee that. But if you wish to guarantee that, you can design some other more deterministic scheduling algorithms, but they are certainly more complex than something like that. So that's the question, my answer to your question.
Okay, thank you. Another colleague raised a hand, Yuanqing. So yeah, Yuanqing, you can speak out.
Yeah. Thank you very much for the talk. And my question is about the first principle, randomization. I think it is very good to randomize, and that may simplify the design. But we also want to have the optimal performance. People may have the concern about the randomization. So if we randomize, then we can achieve the average performance, but may not be able to achieve the optimal performance. So what is your comment on that?
It certainly depends on different algorithms, different situations where we actually try to, what exactly is our design. In the case, for example, quicksort, and a lot of other algorithms where randomization actually improves the performance as compared to deterministic algorithms. Monte Carlo tree search, again, a great example where if you actually don't use it, we are not able to play as well as if we use it in the Go playing, computer player for Go, the Go game. Now, of course, if you actually have switched contact to something else, then, for example, the CPU schedule, then, of course, in those cases, randomization will lead to a very simple design, but we do need something that is a little bit better in terms of the performance. For example, in terms of the fairness to different processes. So that means that we eventually will have to say, no, we're not going to use a random way of scheduling the processes. We have to use a deterministic algorithm, such as something called a completely fair scheduler, the CFS. And that is a deterministic algorithm using a data structure to actually sort the jobs or the tasks. And that's something that is completely deterministic, and it's much more fair than a simple random lottery. So it depends on the context, depends on the situation. But the reason I bring it up is because it really simplified the actual design, and it's something that can perform in a lot of cases as well as a deterministic algorithm. In some of the other cases, can perform even better. And if we can actually simplify something and actually performs even better, why don't we introduce some randomness? That's kind of just to make sure that people don't forget that we can actually have this little tool of randomization to see how we can actually design better systems.
Yeah, I agree. So if the optimal solution is very hard to find, then probably the first thing we can do is try randomize the algorithm.
Exactly.
Yeah, and if I may, then my second question is what is the fundamental difference between the layers and hierarchy in your talk?
So the layers in the idea number 2 would be the layers of design in one single system. For example, in a system where you have software and the software is sitting on top of hardware, then you have these two as layers. And of course, softwares, in most of my examples, the layers are within the software design itself. So you have operating system, you have the applications on top of the operating system. Or if you have the network layer and you have application layer or the end-to-end layer on top of the network. All of these are implemented in software, but we're trying to design this so that we can have an interface provided by the lower layers to the application, to the upper layers, so that the upper layer can just use the interfaces to simplify its implementation. But the hierarchical design is more about the distributed system, where you want to design a scalable system. And that scalable system requires way better scalability, and it does involve multiple computers.
Okay, thank you.
Okay, so we got another question from the audience, Jing Fei. The question is, there are four interesting rules introduced in the talk, but you claim them to be some personal conclusions instead of ground truth. So are there a bunch of related studies supporting these four rules? That would be helpful to know.
Well, I explicitly didn't try to call them rules, even though the rules are from the book of Peterson, but I call them guiding principles, or later on, I make it even weaker and call them ideas. And I repeatedly said it's my personal ideas and my personal opinion. Reason for that is because that system design doesn't have too many rules that we must follow, because it is a creative process. Sometimes this particular idea works, sometimes it doesn't work. For example, the randomization idea that we just mentioned, sometimes it works, sometimes it works very well, but some of the other times it doesn't work very well. And however, I would say that one guiding principle stands out that is cutting across all of the ideas that we have is simplicity. So simplicity is something that I believe is very important. We don't want to design overly complex systems. And because overly complex systems typically have a lot of side effects that during the design process we don't even know, and only when we're using the system in production, then we bump into all of the problems that we have. And that's something that I believe is very important. But otherwise, I think all of these are just ideas. I don't think there are other books or talks or things like that talking about these things. I just want to single them out, bring up your attention to these ideas when you're designing your next system.
Thank you. Yeah, we got another hand raised by our colleague, Lin Wanyu. Yeah, Wanyu, please go ahead.
Hi, Baochun, because I like the randomized idea here, because recently I'm doing some research on different privacy. So basically we add randomized noise to the data to protect the data, to preserve the data privacy. And they usually utility and privacy is trade-off. So we will do some calibration to improve the utility. So my question is, in design system, if there is this kind of step to eliminate the uncertainty, or we say to reduce the effect from the randomized.
Yes, I don't think I quite get your question, but I would say that randomization is something that is not exactly the same as when we're actually trying to generate some noise and add the noise in terms of, for example, local differential privacy. Over there, we're not just designing a randomized algorithm or a randomized protocol. We're just trying to protect privacy by adding noise. I think these are two different categories, even though noise, of course, has to be generated in randomization, but I don't think they're sharing any common traits over here.
Okay. Thank you.
Okay, thank you. Yeah. So actually, yeah, we are overrunning the time. So before we close the talk, just want to answer this question by Nelson Hattie. Yes, we will be able to have the recording, and we, with the permission from Professor Li. Actually, the presentation has been recorded and will be available. Okay, so that answers, hopefully answer, your questions. All right, so yeah, in the interest of time, we are overrunning. We owe a big, actually, there's one more question. May we have any practical evidence approach to your proposed real-world system model? This is from, I don't know, Ken. May we have any practical evidence or approach to your proposed real-world system model? Do you want to entertain that question, or it's optional? Your time is up.
So practical evidence to, I'm not sure what that question really requires.
Yeah. Perhaps he starts asking about, do you have any practical evidence? That is, whether you have a real case, for example, a real project, actually implement following your 4 principles.
Well, I believe I have presented a lot of examples. For example, in the pipelining example, we have this SOSP 2019 paper where we are using pipeline comparison to do distributed machine learning, and it's actually part of the real world example because it's PyTorch. So these are all, I think, great examples supporting my statement that these are guiding principles to real design. And all of these examples are, I present a lot of these examples throughout my.
Yeah. Okay. Very good. Very good. So yeah, I think that should end today's seminar. And on behalf of the Department of Computing and the Center of Research Center of Data Science and AI, we thank Professor Baochun Li for a wonderful talk, very educative, insightful, and very, very useful guide, practical guide to our students and even ourselves. Okay, so yeah, if you still have other questions to follow, you can. I'm sure you can send an email to Professor Li directly or through us. We can help forward. Okay, so thanks, Professor Li, again, and yeah, that's the end of today's talk. Thank you for audience for your attendance. Thank you.